about multi-stage programming, SMT has a backend, and we see that there's a small connection there between the way we're accumulating code-like things in the first stage to execute in the second stage. And then we'll see if we have time for other things, but I guess the main focus is on getting the gist of the stage programming, which we finished it on last time with multi-stage relational programming, but this is the traditional multi-stage programming or like functional programming with side effects. So like you can do this kind of thing in Scala, Haskell, Camel, and things like that. And there are test theories for two-level languages, which also capture some of this aspect of like having code annotated in one stage for a second stage. But maybe let's pose a challenge first. So the challenge is, say we have a tower of interpreters that we might have had at the end of the first lecture yesterday. And here we're saying, okay, it's arbitrary, though it doesn't have to be homogeneous. So we have a language as zero, the user-facing language, and then we have a language and one that is interpreting. So this is so we have an interpreter I1 for the language N1 interpreted in N0. So here the tower is reverted compared to the convention from the effective tower yesterday. And then we want to kind of collapse this into a one-pass compiler. And we can kind of set this so that we have as a base N0, a variant of the lambda calculus, and then at each step we can have some reflective operators that allow us to reflect on the previous levels and so forth. And this gives us a sense of this verify procedure and effect procedure. So now I guess in this setup we have we verify down because I reverted the tower to make it more like a conventional tower of interpreters. And so what we want to do is, having this tower, we want to basically collapse it into a one-class compiler. Now, keep in mind that the tower is conceptually infinite. At any point, you can decide to move to the next level. And because of reflexivity, it's not so simple to just kind of string together these things into like having each one of these interpreters be a compiler, but you could start by doing that. That's already an interesting problem. How do you turn one of these interpreter blocks into a compiler arbitrarily? So this kind of questions, like even just what to do for one box, which is the heart of the matter, goes back to the Kutamura projections in 1971 and partial evaluation, which is kind of like a precursor to staging. And the idea of partial evaluation is that, well, the first is that what we want to do is separate the stages by which we get our programs and our input to our program. So for example, here we would have this mixed partial evaluator that takes the interpreter in the source program and produces a target that then takes the input program. So we specialize the interpreter with respect to our program, and that produces a combined version of that program. Now, in practice, for the practical realization of this, like say you wanted to have a SQL engine and you want to turn it into a SQL compiler or something, you can actually do this kind of stuff, but what becomes difficult is this general mix procedure that can take an arbitrary interpreter and source program and specialize it. You kind of want to do this stage a little manually, and in particular, when you do staging, there's this binding time analysis that allows you to tell, which tells you which parts of your original program are executed now and which parts are executed in the second stage. And all staging does, well, most of what staging does, is puts this under control of the user. The user can, the writer of the stage interpreter can decide manually on the binding time analysis, and that kind of sidesteps this difficult issue of doing it automatically. so say you have, let me just, so say you have a program like, okay, so let's do something very simple. Let's say you have a program like f of x equals x plus 2 plus x, something like that, plus 2, plus 3, let's do that. So, I mean, here you would have, if you wanted to optimize this program, maybe rewrite it as x squared plus 5. You would have to kind of, in this case, maybe it's a little bit more difficult because you would have to shift things around. But let's say I even wrote it in this fashion, right? So basically, you would want to kind of say this plus operation, if it's like this, I can do now without waiting to know what the value of x is. And maybe this I can optimize somehow syntactically into the square function as well. So what decides whether this operation belongs to the first stage or the second stage is kind of like, you have to decide, okay, are the operands like constants, can you do something about it? But basically you can imagine having annotated your program like by saying x plus x, this you can optimize, and then this would be just numbers. So maybe I'm going to get ahead of myself, but the way Scala does it with types is to say you have x would be of type reprobant, meaning it becomes an int in the second stage, and you can have operations on reprobant, so maybe this will simplify to something. And then when you have the plus 2, 3, for example, these are just operations on int executed now in the first stage, so it will naturally do this separation. So that's kind of what traditionally binding time analysis was doing, annotating your operation as either static or dynamic, and your inputs as either static or dynamic. So I'm going to come to a demo, and I think maybe that's a good stopping point. So the conclusion up here is that a stage interpreter uses a compiler, and we can get into the staging aspect. So we could either have like a multi-level lambda calculus where you annotate operations like application with a level here B, or like the level could be something like static or dynamic, or it could be an integer like level 0, level 1, level 2. The lambda is also annotated, or you can have quasi-quote annotations like in MetaML. So this means that you're quoting some code. This means you're splicing in some code, presumably in a bigger context. You can run some code. And then as we've seen in logic on this regime, there is T, the extract of T. And so I'll get to how we turn interpreters into compiler using staging, but first I'll just do a more broad, I mean, I talked about it in the context of the frequent mirror projection. Maybe let me see if it makes sense to talk about this. Yeah, let's just jump to the demo and come back to this. So for this demo, what I'd like to do is basically have this nested array representing a matrix. So some rows are dense, some rows are null, and some rows are sparse. And we can kind of write a vector matrix prod, not too surprisingly, with two nested for loops. And this is all in Scala, and then you can have an input matrix like A1, and then you get the result here. And this is something I can change. For example, if I change this, I get a and it's kind of pays off to think of this as a mini, like maybe interpreter is too strong a word, but really it is something we want to specialize. So we have a matrix that is known and think of it as your interpreter program, and you want to specialize it with respect to a vector that is unknown, and that happens pretty often if you do like hidden Markov models or other kind of matrix-heavy operations. You often know the matrix and not the vector. Yeah.
Just to the regular parentheses are for indexing in Scala?
So this is just a constructor. So the regular parentheses here can be for indexing. I think it has multiple purpose, but it's really just the sugars into an application call. Yeah. So think of it as basically when you're indexing like this, you're kind of doing a hidden call to an apply function, and that can be specific to a field. Yeah.
On the previous slide, there was a rule for programming.
Yeah.
And I just wanted to ask this maybe basic question. In that context, if this is came from an email, I know that that's in the
Yeah, I think there's a relationship. So run means take a piece of code and execute it now. So you're kind of shifting the stages from it was second stage stuff, it was code, and now you're executing. It's kind of important to have that mechanism at the end to be able to run the code. And so implicitly it does have an eval to do that. Yeah, so this is so if you're interested in MetaML, like a good project to look at is Metaprogramming, but I think so Metaprogramming is a good one to look at. And basically you can have something like I have this piece of code, so x plus 2, and now I have this let me call it C. And now I can do C. That would make sense in that context. You need to be in a code context to be able to splice. So it's very similar to quotation, quasi-quotation, like splicing things with quasi-quotation. Yeah?
I know that the approach you're describing allows this arbitrary number of stages, but is there a limit or number of stages in practice that a lot of widely used approaches with metaprogramming tend to have?
Yeah, absolutely. So in practice, people use 2 stages, and most systems are designed to only run 2 stages. I mean, this was like, this one here was a theoretical model where you could think of having multiple stages. In practice, even if you wanted to run multiple stages, you would often do it in steps. So 2 stages is often what you use. But it's kind of an interesting question as well to think of, like, the more stages you have, the more reasoning you have to do across these different levels. So that's kind of a tricky question. Okay, so let's try to do this challenge and of generating specialized code for this matrix. So first I'm going to just put in the code snippet, so the little magic that is equivalent to the run really, but in the context of Scala, what we're going to do is do this code here. And so if I save this, and I can see that now I basically got exactly what I have in the snippet, but as generated code in the second stage. And notice that the ref starts to make its appearance, so we're saying that this V here is something that we don't know in the first stage. It's something that's going to be an array of ints in the second stage. Okay, so what can we do with this? So for example, I can put a condition in here and say like 2 times 3 less than 10, for example. And because that's true, if I look at the generated code, so it really did compile and we get exactly the same thing because this condition is staged away. And that's, as you would expect, this is an if, right? So it's an if in Scala, so it gets staged away. But if like here I put b.length, for example, then I would get something more complicated. I get a condition of the conditional is here, and we've simplified the operation a little bit. Here we get a 6 instead of 2 times 3. And we do get the println and we get the else branch. So the code is not like super optimized, but you can get a sense of what it's doing. Yeah.
Is the node and static still a
Yeah, so there is a common sub-expression elimination that is done. One that is aware of the fact, so it's not going to, if I print hello twice, it should be aware that this should happen twice. But other than that, it's kind of doing what they see that time. There's variants of this framework, which is called lightweight model staging. And this is, I'm using the old framework for Scala 2, but one of my students, Cameron Long, is working on porting it to Scala 3. And this framework is used, the old version uses this single assignment. And it's kind of nice for analysis. Okay, so what can we do now? So now we can try to stage the matrix vector prod. So I'm going to put this inside the snippet here. I mean inside, I'm basically putting it here so that it's inside the snippet, the driver that has the rep types. And here I want to change this to a rep type because that's what I'm going to have. And now there's a few state of hand. So the first thing is I have an actual static array, but I also want to access it dynamically in the code as a way to pass it in. So I'm going to do the static data of the 0. And then here I don't actually want to create an array in the first stage. I want to create an array in the second stage, so I'm going to do that. And I think that's pretty much it. Now here I can call my matrix vector prod. And the A is known from before. And oh yeah, okay, yes, I can delete this part. Okay, so now on this path, so what do we get? Okay, so we got some code that is not straight line. We're getting these nested while loops, and that's because that's the shape that was chosen here. I have a range, and here this was actually kind of a rep of range because I didn't do anything with it. But let me sort of put it into a range as well, and then we get straight line code. And we got, like, we don't have multiplication by 1 or by 0. These got staged away, and that's what we have. Yeah?
So just to reiterate people, this is to turn code that was at runtime doing multiplication with the array by doing all the logic into something that the array value is encoded in the
Yeah, so it's in this case we are also passing, I guess in here we're not passing anything, but yeah, the shape, the array values are encoded in the specialized code that is generated, or like part of the specialized code that is generated, and the vector is not known. But let me bring back the loops for a change. So the problem is if we have the loops, then we kind of have to pass in this extra information, which is what is the array that was known. And here we haven't really specialized too much, we've just recreated those nested loops. But the point is that this array kind of has to live in two worlds. It has to live in the first stage, it's there, but it also has to be reflected in the second stage. And so let's go back to this shape again. I want to keep a range here. And now what I want to do is, I kind of can do some computation here to decide whether I want to roll or unroll. So recall that our array was, we had some rows that were dense, some rows that were not, some rows that were sparse. So maybe we want to have a condition that says, here, if we have, looking at A0, the actual array that we have, if we count the number of, if we do A0I, we count the number of times we have non-zero entries, and this is less than 3, let's say, then we want to say it's sparse. And for now, I'm going to do a code duplication. I'm going to say if sparse, then this times that. So here we want to keep it like this, and here we have the same fixed parts do that. And now we can see that we get one loop and straight line code, and so it's, yeah, I mean, I guess if the array was bigger, that would also make more of a difference, but we got this shape for the generated code. Yeah.
Why don't we always mark everything as a range? What's the downside or what's the?
Well, I mean, I guess in general, so in this case, because it's fairly short, in general here, it's, you can imagine if you had an array with like 1,000 entries, maybe it's better to do a loop at this point. But it's just for illustration purposes, I guess, we see. Yes?
I have two questions. So the first one is it seems to me like the idea is that we're just writing, we're not just, but like we're writing a compiler basically that's like generated based on like the structure of our code. Is that roughly correct?
I think that's fair. That's kind of what specialization, that would be a characterization of specialization. And I think one of the messages that maybe we'll come across with other examples is that you're kind of not writing the compiler directly, you're writing something that looks like an interpreter. So here, well now it's more complicated with the Spark stuff, but if you're writing code that looks like it's interpreted, and it is actually interpreted in the first stage, and you get the benefits of a compiler by having this code generation happen as a side effect. That's your first, you had another?
Yeah, the other one is probably more stupid, but it's where are these like numbers coming from? So the val x14, x17 stuff, like what are those numbers?
Yeah, so I guess, I mean, it's kind of doing them, yeah, I mean, it's not really interesting, it's just like a fresh counter node, you know. So you could also do a better job with naming those things, I guess. But it's kind of hard to keep whatever names you had in the original code because there's such a separation. Yeah, that's a Boolean value, and it's actually where is it used? Oh no, that's weird. So it's not a Boolean value; it's an assignment. So you don't. It's actually just. It's actually doing this part of the computation where it's assigning. And yeah, it's kind of uniformly giving it a name, but it doesn't need to. So it's not a Boolean value, it's an assignment. It's assigning to this output vector here, x2. It's assigning one of the indices to something. To x21, x2 index.
And then x17.
Yeah, yeah. So this could equally be like you could write, you could have it in like that. Okay. Any other questions? Yes.
I guess I'm just wondering if there are any like formal or more concrete results. I think this is very cool, but it seems sort of like you would have to build some intuition as a developer to say, oh, I do want to allow this part of my code to unfold, or I don't want that part to unfold. And I guess I'm just wondering if there's any sort of, and maybe this is what you were saying before, that's where you've lifted that problem out to the developer.
Yeah, so sometimes you do want to control. In many cases, and I will see when we turn interpreters into compilers, it feels very mechanical to do it. I mean, in some sense, actually, like, Scala is doing a bit of the heavy lifting. We saw that when we had, so for example, this if is operating on Boolean, so this is not part of the generated code and things like that. It's basically using its type inferencer as a binding time analysis and checking. And if it has things that are reps, it's going to propagate them as reps. If it has things that are ints, it's going to propagate them as ints. So there is a bit of lifting that can be done with like types with the static compiler. And then the question is on top of that, do you want more or less control? Yeah, so I'm gonna use regular expressions
Okay.
because they're they're pretty simple. But just to finish this off, so here we have a little bit of code duplication, and we can kind of have a staging time abstraction to have here. So let's say this is something you write once in your library, and it does this thing of saying if the condition holds, then you do the range. Then you unroll the range, otherwise you make it the right range. And you can now use this here by saying for unroll is sparse. So okay, so the code hasn't changed. I think this has compiled, and the code hasn't changed, which is exactly what we want. We just created this staging time abstraction to help us think about these cases. And so, in the domain-specific context, this is a useful thing to have, and you're just using the full power of the language to compose your abstraction. And you don't have any, like this is kind of the abstraction without regret part. You don't have any regrets in the performance of the domain. So let's look at regular expression. Let me just quickly summarize this with the slides of turning interpreters into compilers, and I'm going to use the example of regular expression. So we saw that staging is a process that produces code, and an interpreter is something that takes code and additional input and produces a result. And so, for example, you can have a regular expression like this, and you can have an input A, B, C, D, and you have a matcher as your interpreter, and the result is true or it could be false. And then you can put these things together and basically have symbolic input in the first stage and actual input in the second stage. So here I'm using code instead of rep, but that's basically the idea. You can have, basically, you make your input symbolic here, and it's going to generate a code that takes it in the second stage and get the result. So how does this realize in practice? So we can do, so one thing to keep in mind is when you use this pipeline to turn an interpreter into a compiler, you do end up with a naive compiler. It's still a very useful starting point, but it's not going to be magically or super optimized. And so what you can do as an example is this regular expression code. So this was code taken from beautiful code. I think it was yes. So Rockbike and Brian turning down. So this is in part of the and it was initially in C. So it's kind of very low level, but we translated it to Scala. But we basically have a match search to match a regular expression to match it regular expression anywhere in the text. So we can match it in the first, or we can basically have a while loop to match after that if we find it. Then we have the match here, which has a few cases to handle dollar sign for the end of match, to handle star and match here again. And then we have a match star and a match card. So this is the plain Scala regular expression thing, and then what we can have these examples for that. So okay, and now what does it take to actually stage it? So really, what we want to say is the regular expression is still known in the first stage, and the text is a rep of a string. And notice that the code stays pretty much the same, and I think I can put them side by side. I'm not sure if it's exactly the same or just pretty much, but yeah, so in this case it's exactly the same. And that's kind of the point that the binding time analysis is done by the type inference. So for example, this if expression is acting on regular expressions, so we know it completely, so we can decide at staging time which of these branches to take. But this while loop is operating on the length of the text. So this is something that will have to be in the generated way. And so we can see that we can stage the rest of the system like this. And so let's look at an example of generated code. Okay, so it's fairly low level. It's not particularly sure for what it's matching. It's matching A and B at the beginning of a string. So we avoided the while loop here. But you can see that it's fairly low level. It's pretty naive, but it's just kind of turning this interpreter, like this regular expression matcher thought of as an interpreter into a compiler.
More of a comment, but it seems like this makes it a lot easier for an optimizer later to optimize the code at a specific call site.
Yeah, so you can stage transformation, so you can start with a naive compiler and stage a result, or you can even do optimizations during staging. So one example of that is, so this one is actually going a step further and thinking of regular expression matchers as equivalent to automata. So first transforming it into a non-deterministic finite automaton, and then basically converting it from an NFA to DFA and doing it as a staged exploration that is like remembering the common states by doing closure compares, because what we have at the end is that we're generating like a function for each state of the DFA, but we're memorizing when we're reaching the same state. So how does this work? It's not quite straightforward. It's like we're kind of utilizing the states, and so basically we're doing this like exploration of iterating over states. So here the types might be more subtle, and it's more of this stage exploration. And basically in terms of generated code here, so the explore NFA is kind of exploring all the case and saying, if we do this knowing that, then we can kind of reduce the set of things that can happen later and things like that. So it's kind of related to parsing with derivatives. And so once we have this this code, so we can look at okay, so we have this. So we can see here that we've generated these like mutually well, in this case it's not recursive, but we've generated these functions that are doing one set of the state and putting them together and encoding each other. Okay, so this is for how to turn interpreters into compilers. And if we go back to our tower, you can see that indeed we can stage each one of those and basically put them together. Then